All right, everyone, let's get this started. 5.4, we're going to finish 3 more examples, 4, 5, and 6. As a recap, in case you were spending all your time on the assignment yesterday, which I understand and I asked you to do, quickly recap what the purpose of these equations were, or rather how to go about them. Depending on the domain, class. Depending on the domain that is given, your answers might vary a little bit, but the main purpose was to get a sine or trig ratio all alone and make it equal to some number. Okay, so every time, Nathan, just type it there. Okay. Every single time we are trying to get a ratio into a number, then use caste rule to figure out, are there any other possibilities? So here are some examples we've done. Always trying to figure out what is this one ratio equal to. Sometimes it's a nice angle, sometimes it's not a nice angle, but regardless, the steps are the same. Example 3, this was a general solution where you had to talk about all possibilities from 0 degrees all the way to infinity rotations, okay? This was a case where I sort of cheated and said you can divide by a cosine 2 theta. I will address how you can deal with dividing by a trig ratio. Since this is not an identity, we just got to watch out for restrictions, that's all. And you'll see what I mean when I introduce some of the harder questions. I think it's this one. When you get a chance to do some of these, some of the harder ones on the back page, you will see that it's so much easier if you do divide by some kind of ratio, but I think we can ignore that for now, okay? Today, as our focus is on 5.4, I'm going to show you some examples where you might have to use some techniques you bring over from polynomials. Case in point, factor. So consider this example. I have a sine squared x minus a sine just x minus 2. And given that, I'm hoping you recognize it already based on the hints that I've dropped or the technique that I know you have to use. This is going to end up becoming sine squared x minus sine x minus 2 equals a 0. And yes, I am asking you to find all possibilities within 2 quote-unquote rotations from 0 to 4 pi. We'll worry about that after, okay? Please consider how we have a square, power of 1, and a constant. Let, using the letter A, equals sine x. If that is the case, you know that this can be rewritten as a squared minus 1a minus 2 equals a 0, and there you have it, we have a quadratic. Factoring. I believe, oops, sorry, what am I doing? I want to believe that this is not beyond your scope, that given a quadratic, you can instantly factor, and bringing the substitution back, you can argue that sine x minus a 2 multiplied by sine x plus a 1 equals a 0. And we're almost there. What does this imply? It implies that sine x must equal a 2, or sine x must equal a negative 1 for this to be true. All right. And what do you know about sine x equals 2? You might not know, but something might not look right about that statement because you've never seen it before. You would have never seen something like that equal a 2. Someone want to take a jab at it? Why does that not make sense? Yeah? Please remember. So I'm going to write the answer. This equation is impossible there is no solution. So you can just ignore it. Why? The easiest way to explain it is by drawing a sine function. If I draw a sine function, the highest point, or the maximum, is a 1. A y value of 2 will never be reached. And so there's no solution. So all we have to worry about is that. And using that same graph, when is sine x ever equal to -1? At a single point. So an x would be there. No other possibilities. I don't have to worry about casserole. So what is the answer to this solution? Well, therefore, x equals 3 pi over 2. That's right. So this will be for one rotation. Remember? So this is plus 2 pi n. The question asks to do 2 rotations from 0 to 4 pi. If that's the case, adding 2 pi n is a solution. So 3 pi over 2 is a solution, and 4 pi over 4. 7 pi over 2 is another solution. Nothing more. You don't have to add that because it gives us a specific domain. It's just this or that, nothing else. Yes? Pardon me? Could the what?
Do you only add 2 pi if it's going past one cycle?
That's right. So if you think about it, 3 pi over 2 is right there. That's under one rotation, or under 2 pi, right? If I rotated once and then did that, that is underneath 4 pi, right? So you don't have to draw the diagram if you don't want to. It's writing this. I can clearly see that 7 pi over 2 is under 8 pi over 2. It's under 4 pi. So I'm good. Any other questions? So here is an example of factoring and polynomial techniques. It still works, right? In the same breath then, you're going to see something interesting. I'd like you to try this and flex your factoring muscles here. A couple of things. You see that the angle is a double angle, so you might have to watch out for it. You might think, oh, do I have to use my double angle formulas and turn it into just a single angle? You could, but notice how all the angles in the question, they are 2x. So you don't have to substitute it if you don't want to. You can just say, pretend that this is 2 sine squared theta minus 3 sine theta plus 1 if you want to. If you don't need to do that, you can keep it in your head. Instead, go straight into substituting. You can say let a equals sine 2x, which means I have 2a squared minus 3a plus 1 equals a 0. Go ahead. I'll give you a few minutes. How about exactly 5 minutes? See how far you can take this. If you can get to the point where you can get 2x equals some angle plus 2 pi n, you're like 90% there. So give that a shot. Okay? Use example 4 as a model and try it. I'll pause the video here. Okay, so assuming you gave it a shot, the factoring goes as follows. We have 2a, minus 1. That means 2 sine 2x minus 1 and sine 2x minus 1. multiply to give you a 0. What does that mean? That means, therefore, it implies sine 2x must equal 1 over 2, or sine 2x must equal a positive 1. And again, so there's going to be a couple of answers that comes out of a positive 1 over 2. So how about I go about this super thoroughly? Since sine 2x equals a positive value, I know that it has to be an angle. 2x has to be an angle in quadrant 1 or quadrant 2. Right? So let's pretend I am dealing with quadrant 1. The acute angle for quadrant 1 would mean, since sine 2x equals positive half, 2x must be pi over 6. And of course, because we're dealing with, a circle, it could be multiples of 2 pi n. In quadrant 2, I already know what the related angle is, pi over 6. So that means the angle that I'm dealing with has to be pi minus pi over 6, which is 5 pi over 6. And that angle can repeat itself every 2 pi n as well. That's supposed to be the angle within sine, whatever theta is here. Since the angle that we're dealing with is 2 times x, x will then be pi over 12 plus pi n. X for quadrant 2 will be equivalent to 5 pi over 12 plus pi n. And this question is supposed to be within the domain of 0 and 2 pi. So we have to go a step further. If I add a pi to this angle, do I go past 2 pi? No, it's within the domain. Therefore, x is going to be pi over 12 or 13 pi over 12. They're both valid. In this case, x is going to be 5 pi over 12 or 17 pi over 12. That's valid. So at this point, there's going to be some of you who don't understand what's happening. Castrol, isn't it supposed to give me 2 angles? Why is it suddenly giving me 4? How does that make sense? It all makes sense if I consider that 2 as a horizontal compression. Okay, so let me explain this after I finish that. This one's a lot more simpler. If 2x equals 1, if I think about the graph, the only angle that gives me a value of 1 will be an angle of pi over 2. And that means x is pi over 4 plus pi n, which means x is going to be pi over 4 as well as 5 pi over 4. So once you have that down, let's talk a little bit about why there are so many possibilities from a graphical perspective. It's going to be very hard to understand just from looking at the numbers. So let's take a look at a picture instead. Is that okay? All right. It's not the best drawing, but work with me here. Okay, so this is normal sine. Since I have a k value of 2, horizontal compression. This entire curve is going to be completed in a single pi. My period is something new. So how about I'll take a different color, a different size, and let me zoom in. I am going to finish like that, right? This is sine 2x. Now, I'm going to erase all this. I'm going to erase the blue part just so I could prove a point. If my angle was pi over 6, because my y value is half, where does that take me? Using green. Half is right here. So that means I have an angle at pi over 6, and I have an angle at 5 pi over 6, and no other solutions. With me so far? Okay. If I were to, let's draw a dotted line. Okay, let's do that. If I were to take a different color and let's do a pencil, let's not make it too thick. If I were to complete a graph, where did my blue go? If I were to complete my graph there, 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 my pi over 6, which used to be here, is now pi over 12. My angle, which used to be 5 pi over 6, is now at 5 pi over 12. Right? And from there, because I am repeating it twice, what used to be 2 answers, it happens 4 times. So this is plus an additional pi, and here is plus an additional pi. I have 13 pi over 12 and 17 pi over 12 happening. That 2x changes the graph that we're dealing with. And so the answers that we get should reflect it. What used to be 2 answers here and here is now 4 because we've smushed it. I've only had 2 answers for this cycle, but now, since I've smushed it, I have 4 answers. They're all part of the same, I guess, discussion. It's part of the same picture, they're part of the same system. I hope that you will be able to make sense of that. Okay? And the same applies for here. I only had 1 answer, but because I've smushed it, I have 2 locations where I hit a maximum of 1. Okay? Any questions? Yes?
Where it says quadrant 1 in that square below that?
Mm-hmm.
No, like up in the green where it says quadrant 1. Q1, yeah. I'm just kind of, I got lost at the part where you started writing out that equation below it.
Right here?
Yeah.
Okay.
So could you just like...
Sure. All right. So from this factor, I was able to pull out sine 2x equals 1 over 2. It has to equal 1 over 2 so that when you multiply it by 2 and then subtract it by 1, this entire bracket becomes 0. Now, if that was the case, what if I did this? What if I said sine theta is equal to 1 over 2? What is that theta? 30 degrees, pi over 6. Well, are we dealing with theta? No. What was inside that bracket wasn't theta, it was 2x. Well, if theta equals pi over 6, that means 2x must equal pi over 6. Right? And that's where this came from. 2x equals, so sine of 2x equals half. Well, the angle I dealt with must be pi over 6, which means the x value must be pi over 12.
So then why do you have to plus 2 pi and next to that?
Oh, because if an angle is pi over 6, it could be 2 pi plus pi over 6. Coterminal.
I thought like the restriction, the domain said that it was just 0 to 2 pi.
You're right. However, I noticed that the angle was 2x. I knew I had to divide by a 2. Long story short, if I didn't have a horizontal compression, 2 pi is right there. It's one rotation. But since I know that it's going to be smushed, I'm going to have 2 complete cycles within 2 pi. So I have to find my answer from 0 to pi, and then find another set of answers from pi to 2 pi. And so I put that in seeing that about to happen. Yes?
Can you show how you got the 13 pi over 12?
Sure. Well, assuming that I know there's only one extra cycle, we have pi over 12 plus 1 pi. So n equals 1, just one cycle. Well, adding fractions means I need same denominator. That's all. So 1 plus 12, 13 pi over 12. Okay. These are good. Any other questions? This, what we're doing here is essentially the encompassing of everything we've done in chapter 5 plus factoring, right? We have looked at how to make an equation equal to 0, okay? We have looked at cast rule. We have looked at horizontal compressions. The one thing I'm going to do for you for, so how about I organize that thought, okay? To try to help you understand that we're not doing anything new. This is using your polynomial skills to identify, let's do this as yellow, to identify some ratio equals a number, right? It helped us calculate this thingy. Let's call it like, and we'll call this like. And in doing so, we are using cast rule to figure out what the angles actually are. And sure, because the angles are a little bit more complicated with the horizontal compression, you have to think a little bit more too, right? And same with that. It's going to be like this all the time. But the next example I'm going to show you, I really hope you still believe that this is all happening to be the same, except since we're talking about factoring, what if I give you something that's not factorable? Right? It can happen, but you will still see that I have some ratio, and I'm going to look for some angle, and I'm going to use cast rule and so on and so forth. Okay, so let me do all the thinking for example 6. I'd like you to follow through and try to be like, okay, what is Mr. Kim doing? Okay, he's trying to get the ratio isolated. Now he's trying to find the angle. Now he's trying to use cast rule. Now he's trying to so on and so. Just try to follow my process. Okay, you don't have to do it. You will get to do it at some point, but try to follow the process. Here we go. Ready? Now this is me recording for the second time because my first period class I wasn't fully awake. I was making lots of mistakes. If I make more mistakes here, please call it out. Mistakes that you see as obvious. In this example, I am asking for angles that are from negative pi to 0 as well as 0 to pi. What does that mean? It means what are the angles from here, so quadrant 3 and 4, as well as the angles here in quadrant 1 and 2. You would think, isn't that the same as asking for the angles from all 4 quadrants? Yes, but how you present it might be a little different because I want the left side of the y-axis and a little bit of the right side of the y-axis. Okay, here we go. Problem. I see a double angle with a single angle. We have to figure something out so that we can use our identities, or we can do something to make this a little bit more simpler. Right now it's a little complex, so maybe I can use my double angle formulas to turn it into some kind of equation. It's a little more simpler than this. I'm going to try. So we have 3 sine x plus, since this is sine, maybe I will turn cos 2x into a form of sine as well. 1 minus 2 sine squared x, and how about I do just minus 2 equals a 0. Let me open this up. I will simplify it. This becomes 3 sine x plus 3 minus 6 sine x squared, sine squared x minus 2. And if I were to rearrange it so that my squared term is first, minus 6 sine squared x, positive 3 sine x, and 3 minus 2 is a positive 1. Okay. Impossible. Okay, you can't factor it. So I'll put a little thing here saying not factorable. Okay, so I'm going to test the discriminant just in case. So b squared, that's a 9, minus 4 minus a, and sorry, minus 4 times a times c, that is 9 plus 24. It's a positive 33, therefore it exists. Okay. May I continue doing it this way, or would you like me to substitute so that it looks like a quadratic? Substitute? Sure. I'll use a again. Question, Everett?
Yeah. Why can't you common factor that?
What would be common? Yeah. No, I'm not laughing at you, but like yeah, you take a look. If you want, Everett, you can divide out or factor out a negative 1, right? That would become a positive 6 minus 3a minus 1. I mean, you could, right? So here's what happens, right? If you follow quadratic formula, so I didn't use x squared because I don't want you to be confused. A must be negative b plus minus the discriminant divided by 2 times a. It's that. And also, so that you won't get confused, I'm going to bring this back. Sine x equals this. So let me solve that for you. We've got negative 3 plus root 33 divided by negative 12 gives me a negative 0.23, or sine x equals negative 3 minus root 33 divided by negative 12. That's a positive 7.28. If sine x equals negative 0.23 or sine x equals 0.73, it would make this equation equal to 0. They're not the prettiest numbers, but that's okay. What angles give you negative 0.23? What angle gives you a positive 0.73? Let's do it. Inverse sine of negative 0.23 is approximately, oh, interesting, negative 0.23 radians. Whoa, coincidence. Inverse sine of positive 0.73 equals 0.82 radians. Something I forgot to do. Since the sine value is a negative, it can also be in quadrant 3. So to visualize, I'm going to draw something here. This angle is in quadrant 1. If sine x equals positive, it's also in quadrant 2. So what does that mean? Well, if this angle happens to be 0.82, by cast rule, if that was 0.82, what is this angle? How do I calculate this angle if my acute angle here is 0.82? Careful, it's not 2x in this case. We are all working with just x. You don't have to worry about that. We are now dealing with just 2 pi. So 180 degrees in this case is half of my cycle. The angle for quadrant 2 would be pi minus 0.82, which is approximately 2.32 radians. And the same way, if I'm dealing with an angle of negative 0.23, that is equivalent to saying my acute related angle is 0.23. It's the same thing. So if I am now in quadrant 3, and this angle happens to be 0.23, what is that angle? And I'll tell you right now, it should be a negative angle because I'm going backwards. But if you don't like negative angles, go positive and then take away 2 pi. You can do it so many different ways. The answer is negative 2.91 radians. Here's the final answer. I have 2 degrees, 2 different angles in between, so in negative pi to 0, x is going to be negative 2.91 radians or negative 0.23 radians. And from 0 to pi, my angles are going to be 0.82 radians or 2.32 radians. Well, let's all hope that you don't have to deal with quadratic formulas too often. Okay, you want to go up?
No, down.
Down. That's the last bit. This is it. Okay, but again, I'll come back to this, but I just want to show everyone we are still going through the motion of trying to get a trig function all alone to equal a certain number. Right? So how about I highlight this as yellow because we are doing some trig techniques. We have identified this as the solutions that we need to solve. We have used CAST rule. As we did before, giving us our final solutions. It's the same stuff. Once you get more practice out of it, you will be able to recognize why we are doing the things that we are doing. But for the moment, my recommendation is start with the textbook questions that get you to work through equations similar to examples 1, 2, and 3. Once you get the hang of it, I think you're ready for factoring style questions. And once you get the hang of that, you might want to try questions that don't give you nice numbers. Got to baby step into it. Don't expect yourself to jump into example 6 right away. That's saying you're setting yourself up for some rough nights. Yes, absolutely. Question?
How do you know that the number is about within radians and not
The number itself is a normal number. When you do the inverse, it's a matter of how you set your calculator, right? So this is a normal number, but when I did the inverse sign, the answer I got was in radians. It will give me a degrees, yeah. And you work with not pi and 2 pi, you work with 180 and 360. Same stuff. Okay, I'll stop the video here.